In this problem, we want to show that the flow between the plates has a stream function but no velocity potential. And you can see I've drawn the picture that we have, and you'll notice we have a linear function between the plates. We're going to call that u. It's going to be a function of y, so y is the vertical distance as we go up. H I have denoted as the total distance between the two plates, and you'll see that we're going from a velocity of u equals 0 when y equals 0 to u equals a velocity v when y is equal to h. So we need to write that down because we'll be using that. So at y equals 0, our velocity in the x direction, which is u, is equal to 0. And at y equals h, u is going to be this capital V. Now, we need to get this equation of the velocity as it increases as we go up in height. So to do that, since it's just a linear function, we can write that u is equal to my plus b. And we've got two data points that we can use. We've got this initial point at y equals 0, and then we've got the final one when y equals h. So let's go ahead and use that. Let's start out with the bottom point. So at y equals 0, we can write that u is equal to 0. That's got to equal m times 0, because y is equal to 0, plus b. So from this equation we get that the y-intercept is obviously 0. And then do the same thing for the upper point where y is equal to h. If we do that, our velocity there is going to be the capital V. That's going to equal m times y. Y at this case, at this point, is h. So we'll put h there. And we already found that b is equal to 0, so we can just put 0. So from here we can get our slope of the line. So the slope m is going to be that capital V over h. Now we have our function of velocity. So u is equal to the capital V over h times y. So here's this. So that'll be our velocity in the x direction, and our velocity in the y direction, which would be the lowercase v, that's going to equal 0, since all of our flow is in the x direction. That'll be important to realize. Alright, so now we've got that. Now we can start looking at the stream function and velocity potential. First of all, we need to know if we satisfy the continuity equation. Let's check that. So the continuity equation, we have the partial of u with respect to x plus partial of v with respect to y. And we need to ask ourselves if that's equal to 0. The partial of u with respect to x, using this equation here, is going to be equal to 0. Alright, so let's write that down. And then the partial of v with respect to y, where this is v, that's obviously going to be 0 also. So we'll put that as 0. Obviously 0 plus 0 is equal to 0. So that checks out. So from there we can go ahead and look for the stream function. So we know that the partial of the stream function with respect to y is equal to the x component of velocity u. We've got our equation for u, so we can set that equal to the capital V over h times y. Now from this we can cross multiply and solve for the stream function. So we cross multiply. We've got d psi equals vy over h times dy. Integrate both sides, and you get that psi is equal to vy squared over 2 times h, and then plus some constant c. So that'll be our stream function. We found that. And now we want to know if we have a velocity potential. So in order to have a velocity potential, we need to have the curl of the velocity vector equal to 0. And remember, the curl of the velocity vector tells us about rotation. So if the curl equals 0, that means we have irrotational flow. And we can only have a velocity potential if we have irrotational flow. So let's check this out. Let's write out what we need here. For 2D flow, the part of this equation that we really care about is the z component. The x and the y components automatically go to 0 because we do not have anything in the z direction. So we're just going to focus on the z direction, or the rotation about the z-axis. So here we've got the partial of v with respect to x minus the partial of u with respect to y. Those are your k components. So let's see what we get here. We already said our velocity v was equal to 0. So here we're going to have 0. And then we need u with respect to y. So the derivative of u with respect to y, if we look up here, is just going to be v over h. So v over h. Now obviously 0 minus v over h is not equal to 0. So this is not equal to 0. And that tells us that we do have rotational flow. And if we have rotational flow, that means there is no velocity potential. So in this case, we had a stream function but no velocity potential. And it's important to realize in these type of problems, when we have a 2D problem, that for rotation we really just care about the rotation about the z-axis. That'll save you some time on a test or a quiz if you remember that.